Okay, good. Yeah, could I have those pens, please?
Oh my God, that's right. Is that in the next chapter?
Yeah, that's good. Okay, so this is continuing what we did last time. We were talking about this Bytonic Tsp problem. And the problem is you're given a set of points in the plane, and you're asked to find something called a Bytonic optimal Bytonic traveling salesperson problem, as a salesperson tour. And the idea is that if you start at the leftmost point, you can only go right, and then you can only go left, and then you should be done. And in those two parts, you should cover all the vertices that need to be covered. That's called a traveling salesperson tour. A traveling salesperson tour needs to visit all the vertices. A Bytonic traveling salesperson tour only makes one sweep in both directions and gets back to the start point. Okay. So this is an example that's not a Bytonic tour, and this one is. And our goal is not just to find any Bytonic tour, because those are easy. Our goal is to find the optimal one, right? And this problem is given both in the VJudge data set as well as in your Corman book. So whichever one you want to look at, that's fine. So I think we kind of talked about this last time. We're going to set up the dynamic programming in the following manner. We're going to sort the points from left to right, meaning using their x coordinates. So the leftmost point is going to be called 1. Rightmost point, wherever that is going to be n. And we're going to build not a regular Bytonic tour, but we're going to build partial tours and keep going forward, right? So we're going to call Bij as the best possible tour. I forgot to add the word best. Yeah, so it's the optimal tour where one of the pieces goes up to I and the other piece goes up to j. So you're building part of the return path as well as part of the forward path. The only thing you need to know is we're going to assume that j is bigger than I, and all the points between 1 and j have been covered. You never have to worry about them. They're all part of the tour somewhere. Okay. So now we have to kind of figure out how to take care of j plus 1 and so on and so forth. The strategy, of course, is to try and design a recurrence relation or design a recursive solution, whichever works out for you. In this case, we're going to jump straight into the recurrence relation. And I can show you the rest of the pieces if you want later. For now, let's just say how to set up the recurrence. And I think you guys may have figured this out, but let's see if we can picturize this so that we understand this better, right? So the first case is when I is less than j minus 1. So there are a bunch of points between I and j that are only on the lower path. Okay? If they are only on the lower path, then it becomes easy. Because now this Bij, we know that j minus 1 has to be on the lower path. So therefore, Bij is Bij minus 1 plus this last edge. Okay? So this is the easy case. As long as I is less than j minus 1, there is no other way that can be done. It has to go this way. Everything between I and j must be part of this path, the lower path. Again, I'm just calling it lower here because of the picture, but really there are two paths. One is a little further ahead than the other, right? Okay, so the second case is going to be what? if we have taken care of I less than j minus 1, there is only one other case possible, and that is when it's equal, right? So we've taken care of that. We're going to now take care of the case when I equals j minus 1. Now what happens? Well, at this point, it's kind of unclear what goes on. This last edge on the longer path could connect. It's not going to connect to j minus 1. That much we know. It's possible it connects to j minus 2. It's possible it connects to j minus 3, j minus 4. Anything is possible. In fact, it could even connect directly to 1. And we just let all the other points be picked up by the shorter path. Right? Does that make sense? So if you do it this way, then your recurrence turns out to be there is some point k over here that's going to be directly connected to j. So you're going to get that distance k to j. And then you just remove this edge, the last edge that you added. The remaining is going to be kj minus 1. Remember now, this guy is going to be further ahead than the lower one. So your recurrence will say b of kj minus 1. So k could be j minus 2, j minus 3, j minus 4, whatever, we just don't know. These are your two cases. Did that second one make sense, or should I explain this a little bit more?
So in this example, you're not considering I being greater because they cross?
Well, I assumed I is actually less than j.
Yeah.
Yeah? So this is an assumption. In fact, I'm always going to write this as bij, where j is bigger than I. And so if they're out of order, I'll flip it, because I don't care about the b of j comma I. So if I is j minus 1, then really what we want to do is b of j minus 1. B of j minus 1j is what I want to do. So I have 1 here somewhere. One path goes all the way to j minus 1. The other path goes all the way to j. There are no points between this and this, right? But we just don't know which one this guy is connected to. It may be j minus 2, it may be j minus 3, it may be whatever. The remainder goes on the other curve. So we have to now iterate over all possible values of k. I'll call this k. And then set this up. So let me show. I had some animations here. So it's possible that k is j minus 2, in which case this is exactly what it's going to look like. It's possible that k is j minus 3, in which case I remove these 3 blue edges and make those 2 red edges, right? Or it could be j minus 4, in which case it would look like this. The green edge would come here, and then the rest, and then the top curve would take care of the remainder, right? So it just depends on where you're going to patch it. So all you have to know is, what am I connecting this j to the left of I? That's all I need. And there really aren't any other cases. Okay. So setting up the recurrence is pretty much all you need. There is one special case. You have to kind of figure out how to end this whole thing. And so that's the same as asking b and n. So b and n is actually just a special case of bn minus 1n, where I add that last edge. So it's a very simple scenario, and so essentially you're saying I have one path that goes to n minus 1, the other path goes to n, and now all I have to do is to add this edge. Now you might wonder what happens if n minus 1 should have been on this path. But then that's actually symmetric, because then if n minus 1 should have been on this path, then I would take this off and add this in, and I would get the other bn minus 1n, which is the same as what we wrote down. So this is just a simple addition at the end. There is no cases to consider. So all I have to do is to figure out everything from b. In fact, the earliest I have to start is b12, and I only have to go all the way up to bn minus 1n. I don't need anything else. Hey, David. Does that make sense? So yeah, it's worth. So here is the actual pseudocode. If you need to look at this, we're of course going to sort them by x coordinate, right? That's the initial setup. We're going to set up the base case. The base case is b12. Now think about what b12 is. I got 1. So one of the paths is empty. There is nothing to take care of. The other one has 2 on it. So really, this is the only way you can get that started, right? So this path here is empty. Nothing more to take care of here. So b12 is simply the length of this edge. That's what it says there. And then you set this up for j equals 3 all the way to n, but you only go for I. So remember, there are two cases when I is less than j minus 1 and when I is equal to j minus 1. So I'll go first all the way up to j minus 2. And these are easy to figure out. If I is 1 through j minus 2, then we know that the formula simply says add that last thing to, well, it's going to be part of the lower curve, the longer curve, right? So this is the easy case. So the only thing we have to worry about is when I is j minus 1. And when I is j minus 1, we have a loop to figure out. So we're going to initialize that by saying set k equals 1. If k equals 1, then we get b of j minus 1j is b1j minus 1 plus d1j. Let me remind you the recurrence relation looks like this. So you have b of j minus 1j is b of kj minus 1 plus d of kj, right? That's the recurrence we want, and try all possible values of k. So David, do you need a quick thing to catch up? Should I show you? Should I quickly tell you what we did?
Yeah.
Yeah? So we're taking, so first of all, what is Bij? Bij is the optimal curve where one of them ends at I, the other ends at j.
So one path goes to I, one path goes to
Goes to j.
the leftmost.
From the leftmost. And you have to cover everything from 1 to j. And the only thing you need to know is that I is less than j, strictly. Okay? And it turns out that there are two cases, and those are the two recurrences. One case looks like this, the other case looks like this. And the first one is a simple computation. The second one requires looking at a whole bunch of different possibilities. So that's the code that we are trying to write now. Yeah. So now we're setting up the loop for k. We already took care of k equals 1 here. We're doing this from k equals 2 to j minus 2. right? And it's the same formula as before. Instead of 1, you have k. So you're going to have b of kj minus 1. So sorry, so you're saying b of j minus 1j is b kj minus 1 plus dkj, but you only do that if it's better than what you've seen so far, right? And so you're simply looping through all possible values of k, and at the end, you report b of n comma n, which is adding that last edge from n minus 1 to n. And that's it. Okay. Now, I've been trying to see if it's possible to do this more efficiently, but let's quickly look at the time complexity of this. What do you think is the time complexity? Why is that? Shouldn't it be n cubed? Because you have to fill up n squared entries, and there are several cases where you have to try different possible values of k.
Yeah, but you only consider that one case by itself. Not
That's right.
For every single BIJ.
That's right. So that's something that's not usually clear for most people. So this is the only part where you have to do a loop, and that's for only one of the items. So only one of the items takes big O of n time, but all the others take only constant time. And so therefore, this whole thing only takes you order n time per row, which is exactly what you want. And so the whole thing runs in n squared time. And so really, then there is a challenge in terms of reconstructing the path. So have you guys thought about this? No. Yeah. So that's actually a bit of a challenge. You want to spend a couple minutes thinking about this? How do you massage this to actually give us the path? Sorry, it's going to take us let me finish this problem and then catch you up to speed, okay? So you may want to just think about the picture we had here. Yep. So these are the cases that we looked at, and we need to know how to now reconstruct the path after you've done all your b of n comma n. Or if you prefer to look at the code, that just takes this recurrence and ends up computing it. Okay, oops. Come on. All right. Okay, any thoughts about how you're going to reconstruct the tour?
So one thing, maybe, so store another array.
Mm-hmm.
When we update Bij,
Yeah.
we store,
Right.
we have basically the case where, let me see, j minus 1 is connected to j minus 2.
Yeah.
So when we probably store for that point, maybe call it Aij,
Yeah.
store j minus 2.
Right. So good. Yeah. That's another way to think about this is that your Bij in this case is straightforward. It's only in this case that you have to kind of worry about it. But depending on which k you picked, if you can remember that k, then you're in good shape. Then you can reconstruct this. So really the trick is to keep track of the k that was the winner, right? That caused us to update the formula. And once we do that, it's effectively you can reconstruct the tour after that. Because then from bnn, you'll go to bn minus 1n. That'll tell you which k you used and where you went. Once you do that, part of the tour becomes easy, right? So let me draw that here. So let's say this is the optimal tour, right? Here is 1, here is n. Somewhere here is n minus 1. We can remove this edge because we know it's there for sure. So we look at bn minus 1n and figure out what value of k was applied in order to get this optimal solution. And that'll tell us that, okay, you connected n with this k. This was the last edge. If that was the last edge, then everything between k and n minus 1 should be on this path. So you kind of figure out all the guys over here. And so you will come all the way up to k plus 1. And now you're going to look at b of k plus 1 and ask, what value did this guy connect to? And that'll say, okay, I connected it to that one there. That might be some k prime. That means everything from k prime to k should be over here. So you do this and you reconstruct the tour. Did that make sense? Okay. All right. So what's your name? Katya. Okay. So for Katya, let me just quickly tell you what we did here. So we were looking at the Bytonic Traveling Salesperson problem. And what we said, so are you familiar with the problem?
Well, I was listening to it in the car, but I couldn't get to it.
So quickly, the Bytonic Traveling Salesperson problem says you're given a set of points. You have to find a traveling salesperson tour, which means you have to visit all the points. And you want to find the best one. But among those tours, you only want something called a Bytonic tour, which means you start from the leftmost point. You work your way all the way to the right. You never decrease your x coordinate. You only go right. And then once you're done, you go back left. And among all such tours, you want to find the best one. Okay, that's your Bytonic tour. And then we figured out that there are, in order to do the recurrence, there are two cases. So I'm going to set this up so that bi comma j is the optimal partial tour, where one part goes up to I and the other part goes up to j. And what we figured out was that if I is strictly less than j minus 1, then we know that j minus 1 must be connected to j. Otherwise, j will be connected to something different, which we have to figure out. And that comes from a second recurrence that says it's going to be one of the different possible values of k, which is anything between 1 and j. And we have to figure this out by figuring out which one gives us the best answer. And so those are the two cases you get. This is essentially your solution. And from here, you can write the code that actually achieves this. And this is the pseudo code that achieves this. Okay? That's the rough idea. You can go and listen to the stream again and figure this out. Any other questions? Seems doable, no? Wasn't too bad, although it is a challenging problem. Yeah?
So just to make sure I understand it, so when I is equal to j minus 1,
Yeah.
we want to take a k from 1 to j minus 1, right?
J minus 2, yeah.
Okay, everything before it.
Right.
Okay. All of that is to be added to the top half.
Yeah.
Okay, that's it.
Yeah, okay, sure, yeah. So that's why it's worthwhile to just think about this picture, because it pretty much takes care of the two cases. Yeah. So here, if I is less than j minus 1, then j minus 1 is going to sit somewhere between, and there is no choice. You have to connect it to this. Nothing else you can do. So therefore, you know what that recurrence is going to look like, which means I have simplified the problem from ij to ij minus 1. My goal is to reduce the problem. I don't want to increase it or make it more complex. So I've now reduced bij, the problem of solving bij, to the problem of solving bij minus 1. That's my goal. The distance, of course, is just the distance computation, very simple. But if I is not less than j minus 1, then I have a problem. Then it looks something like this. Then I just have to figure out where this guy is connected to. We know it's not connected to this because they're separate. Since I don't know which one, I have to try all these possibilities. And that's why I do a minimum over all possible values of k, going from 1 up to, I shouldn't say j minus 1, that should have been j minus 2. Yeah. Sorry. Yeah. Yeah. I need to fix that. I just will do it now, otherwise I'll forget. Okay. All right, done. So really, everything comes from this recurrence relation. But you can also start with this picture and try and write a recursive solution if you want, because you can think of a recursive procedure that computes b for some I comma j, which in turn makes the appropriate recursive calls. So you can set this up as a recursive procedure. That's not difficult. But of course, the recursive procedure is going to be expensive. And so then you have to kind of figure out how to turn it either into a non-recursive one, or figure out how it never makes the same recursive calls over and over again. Okay? Yeah.
So here we're trying to find the minimum of bk to j minus 1.
No, we're not finding minimum of bkj minus 1. It's bkj minus 1 plus that edge. Yeah. Okay.
But that's the part of the question. Why is it plus the distance from k to j, not j minus 1?
Right. So again, let's look at this picture, right? So right, this is what it's currently looking like. Here is here is I, and here is j. Well, let me pull this up a little bit more. Here's j, and j equals, or rather I equals j minus 1. This is the case we are trying to grapple with. What that means is, if I draw these vertical lines here, there are no points in between there, right? Okay, so we know that we have to deal with all the other points from 1, 2, 3 up to j minus 2. And, well, I don't have to worry about 1 because 1 is on both curves. Everything between 2 and j minus 2, either I have to put it on the top path or the lower path. I just don't know which. All I'm going to be concerned about is which one is connected to j, which means what's the last guy on the j path before j. Since I don't know which, it could be this guy k is the last one here, but I don't know what that k is. Now, if k could be either 2, 3, 4, or well, actually it could even be 1, because j could simply be connected here, and you can put everything else on the upper path. So k could be any of these values, and so I have to try them out. Now, what is the actual path length going to be? The path length is going to be this edge plus a partial path that goes from I to k. And that's what you see. That's the partial path from I to k, but I is j minus 1, plus that one edge from k to j. And that's what you see there. Right? Is that clear now?
Yeah.
So it's more a matter of just staring at it and writing it down carefully. There are, of course, many ways to solve this problem. Was your solution quite different?
I found my recursive solution to be just easier to understand for me, the way that I'm used to dynamic programming.
Yeah.
Because when I try to switch it to the recurrence formula,
Yeah, it's in this case it's a little tricky. Yeah.
it's a little tricky because usually
Agreed.
dpij is equal to minimum of 2 possibilities.
Yeah.
Something like that.
Right. Here it's. Were you able to do this with 2 possibilities? No, right?
It was, yes, there's 2 possibilities in the recurrent, in the recursive
Then-
solution.
Then let's hear it.
Right.
You probably want this,
Yeah,
right?
yeah, please.
There we go. I guess I can do it here. So I'm going to define my recursive solution as Bytonic Traveling Salesman. We kind of just want to keep track. We're doing the same thing. We start at position 1. Actually, I'm going to call it position 0, just because that's what I'm used to. And then we have some path I to j. We actually only need to keep track of I and j as our input parameter. So we can say I and j.
Yes.
Our base case is if either of these is equal to, we have up to n, or actually n minus 1.
Okay.
So if either of these is equal to, if I is equal to n minus 1,
Yeah.
or j is equal to n minus 1,
Yeah.
then we just have to find the distance from I to n minus 1 plus the distance from j to n minus 1. We just return that. Or basically we have most of the path,
One of which is going to be 0.
one of which is going to be, yeah, sure, 0.
Okay.
It doesn't, in the code, it just works out fine.
Okay.
But how do we want to add the next point. One of these points has the latest point up to, let's say, k. One of these is k minus 1. So how do we derive k?
Wait, so k is either I plus 1 or j plus 1, right?
Yeah, one of those two.
Okay.
So k is actually just the max. max of I, j, plus 1. So we take the maximum point. One of these is going to be the bigger one. And then add 1 is going to be the next point.
Yeah.
And then we just return the max, actually, of, we can choose k to either be in the top or the bottom. So let's say k, j, plus the distance from I to k, or b I k plus the distance from j to k. And then we just add memoization to this. Our state is I and j. So our state is of size O(n) squared. And then for each recurrence call, we're just looking at one of two cases or three. So it's times O of 1, which is just O of n squared. My initial solution started with keeping track of the largest point, but I noticed that we can actually derive it from I and j, so we decrease our time complexity. Yeah.
So your
Yeah.
computations are simpler per iteration.
Yeah, because in this case, we just two different possibilities, and that's it. When I was trying to switch it for the recurrence formula, then I got some cases where I'm only looking at one, and then it kind of confused me. And then I said, but in some cases, I'm looking at a bunch of previous ones. And then I was thinking of cubic time. So I kind of just thought I was doing something wrong.
So you have to convert this to a non-recurrent, you have to make sure you don't call things repeatedly, right?
Yeah.
So you got to have to figure that out.
Yeah, last one.
Yeah. Why is it the last return?
Mhm.
Why would it not be min?
Oh, sorry. Min, because we're finding a minimum distance. Yeah.
Is d it's the same as this?
Yeah.
Okay.
Yeah, distance.
So it's the same as this, yeah.
And then we just find that with O(n) one time.
Yeah, this works as
Yeah.
well, yeah. So much depends on how you draw your picture and how you set up that reference. Thank you.
So Randy, are you a K-pop fan? BTS?
Right, what did you do of BTS?
Wait, really not that you changed it to English later on?
Yeah. All right, so we have a little bit of time, so let's take another problem. Sounds good to you? So I don't know if we've done this before, but it's called the company party problem. Have we? No?
No.
Okay. Okay, so it's called the company party problem. It's also on VJudge. You can look it up. Here is the, well, there's also a version in the textbook. I think this is easier to read, so let's read this. I'll give you a couple minutes to read it up.
What's conviviality?
Think of it as a friendliness guy or some fun score.
Okay.
Yeah. If you're a good dancer, your score is going to be high. If you're a lousy dancer,
What if you're a lousy dancer? You make good jokes.
yeah, if there are other things that make up, or if you're good looking, yeah, maybe then it's okay. So each person has a fun score, okay, and you want to invite people to the party in such a way that you maximize the fun score of, it's the sum of the fun scores of all the people you've invited. But there's a constraint. What's the main constraint?
You don't want an employee and their supervisor?
Yeah, you can't have both an employee and their immediate supervisor at the same party, because then you're destroying their fun, right? There's also one more constraint. Was that here? In the VJudge version, it said that the president or the CEO also needs to be included in the party. So those are your constraints. First one is the CEO or the top person needs to be invited. And you cannot invite a person and their immediate supervisor, and you want to maximize the total fun score. Problem is clear? So think of your, I just made up names there. And each of them has a score. So whom do you want to invite to the party?
Jamie, Jenny, Joanne.
So one possibility is to go the greedy way.
Yeah.
And say, yeah, Janelle looks fabulous, Jenny and Joanna I like, and maybe Juan, and of course I have to call Jane. So
A hierarchy?
there is a hierarchy, so I can't just randomly call people.
Oh, okay. So what if we did like a breadth first search? You know,
Yeah.
we color that one red and Hyman blue, but then
Yeah.
we color the children of Juan blue, but the children of Jaime red, and then we just pick Jaime.
So you're saying turn this into a bipartite graph and pick one of the teams, and since the CEO needs to be included, what you're going to end up doing is you're going to pick up Jane, you're going to take all these people and throw away the rest. Is that going to be good? That doesn't look too good to me.
Let's say we start at the root.
Yeah.
Right? And wait, do we have to invite her or no?
Yeah, yeah.
Okay.
Yeah, we
So-
cannot annoy Jane.
Let's just, I'm gonna
She
ignore the
pays
case
your
of the root.
salary.
We have one possibilities at any given route. We can
Yeah.
either choose that person or not choose that person.
Right.
So we tried both possibilities and return the match basically as our recursive solution.
Yeah.
And we just add memorization. We keep track of did we invite the last person? If we didn't invite the last person, we cannot invite the current route.
Yeah.
So we just
So
pick that guy.
I'm going to stop you for a bit because I know you're getting there. Let me ask the others. Yeah. He's never going to be invited to the party. So do you understand the challenge here? It's I can't just color it black and white and do this bipartite thing. I can't just take them in layers because maybe this layer is just awful. This could all be 0, right? And then your party is going to be a complete kaput. So we've got to do something smarter. Any thoughts on this?
Wait, yeah, can you go back to that slide of the tree?
Yeah.
So, for kind of what Rich said,
Yeah.
I swear I'm not copying him.
Yeah.
For every child of a node we're looking at,
Yeah.
we do have those options.
Right.
that we
So let's say Juan. Yeah. So what about that?
We need to, so let's say we're looking at Jane, now we're looking at all its children.
Well, let's leave out Jane for now.
Okay.
Yeah.
Okay.
There are only two possibilities: Jane is there or Jane is not there, and we could do both, right? So it's easy. So whether that constraint is there or not, we don't have to worry about it. It's a simple matter. But give me a general approach. Yeah.
Would it matter about Jane because Jane is the immediate supervisor
Of course it matters, but you'll get two you can I mean you could solve both problems and pick the one that you pick the one where the constraint, if the constraint is there, then obviously only one of them works. If the constraint is not there, you can pick the better of the two, right?
Wait.
There's only two options. One where Jane is invited, but then Juan and Jane is not invited. For them, right?
Well, Juan is a different matter. But yeah, let him finish his thought here.
So, okay, for every node we're currently looking at,
Yeah.
we want to look at all its children,
Yeah.
and then add to some value whether taking that children or not taking it.
Right.
If we do take it, then when we explore that child, we cannot take the child of that child, because that's a supervisor
Yeah.
of those. So we need to skip over that later and then go to the next one.
Right.
No longer be the director.
Right. But then aren't you just getting back to what David's solution was? Just do, since Jane is there, we'll just skip the next layer and go to the next following layer and take everyone there. Why is that?
Then, let's say I could or could not choose Jane.
Yeah.
And the same thing for Jenny, I could or could not.
No, so let's say, so think of this tree, okay? Here is Jane, and Jane has 3 children. Well, actually only 2 in this case. That's fine. And then let's say you have something like this, yeah? So if I do have to take this, then you will end up just taking these guys. Right? There is no other choice.
No, but you might take the one on the left and then not take the bottom. It depends on which one gives you the maximum value.
Say that again. So yeah, I guess I need names here. What are you trying to say?
So here, with what, what my idea is, for the CEO, for Jane.
Yeah.
The one on the left, we can either take it or not take it.
Well, if Jane has to be invited to the party, there is no way to invite this person.
Oh. Oh, we have to skip them? So I was thinking at Josh, right?
Yeah.
So we either take that one or take its employees, or the optimal solution at the sub problem. And then we add everything we need, and then like replace it if it's greater than Josh's.
Right. So instead of Josh, you're saying I could replace it with these 2 guys.
Right, yeah.
That seems like a possibility. I could do that with Joanna as well, right? If this core had been bigger. So it seems that there are more possibilities. You can't just go boom, 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 right? You can't just say, okay, this layer is gone, this layer is what I'm going to take. So breadth first search doesn't really work, right?
Does this mean we always have to skip the layer, the children of the CEO of the group? Of
Yeah, unfortunately they're out. Yeah. They're all boring VPs anyways, so it's okay. So, solution. I thought you guys heard Ricky spew out the solution. No? So at least you're getting you're getting there, but how do I turn it into a solution now? It might be useful for you to start to think about the base case and how to make it larger and larger and larger. Right? So what's the base case?
And there are no supervisors.
What is the base case?
I mean, it's not a supervisor. It's a
Base case is when the tree is just this. If there's only one party and one person and this person is the CEO, well, she can have a party with herself. That's it. Right? Now, the next case might be if there are 2 layers like this. Again, it's easy because we have to invite the CEO and the others we have to dump. So the CEO is going to have a party with herself. That's no good. Then, so these are 2 easy cases. There's nothing interesting about it. So there must be at least 3 layers in order for anything interesting to be done. So this is another possibility. And here, what do you think is going to happen? Since the CEO has to be included, these 2 have to be dropped. You might as well take all these people, unless they have negative scores. We're assuming everyone has positive scores. Okay?
So, Professor, was what I said wrong?
So say it again. I can't remember.
So let's say we're on Josh, right?
Yeah.
This is a pretty small tree, so I
Right.
put Josh.
Yeah.
We want to look at all its children, so we
Yeah.
keep track of a value.
Yeah.
So we say that value is going to be equal to its where it currently is. Let's say we set it to 0.
Yeah.
So 0 plus taking Jack or not taking, the max of taking Jack or not taking Jack.
Right.
Then when we get to Janelle,
Yeah.
it's the same thing. That
Either
value-
take Janelle or not take Janelle.
Exactly.
So.
And then at the end, though, we
Uh-huh.
need to check, after checking all his children, the maximum of all his children, or just taking Josh.
Yeah, so the problem with that is, we could do essentially what you said, where you find the best score with and without an employee. The problem here is that it just is 2 to the n possibilities, because everyone either is 0 or 1. Either they're invited or not invited. So how are you saving from things getting to be exponential? Right?
We can obviously memorization, right? That's always
Don't think about memorization. It does not help you, is my advice in general with DP.
But if we keep track of, let's say we're on a current node, right?
Yeah.
And we've taken it before.
Yes.
Can we just look up what the value was when we did take it?
Yeah,
off the recomputer?
sure, of course. Yeah, of course.
So that's
So yeah, memorization, that's all it does for you. It prevents you from redoing problems. But that's not really the hurdle. So but the 2 to the n possibilities are distinct possibilities that are going to happen independent of this. Right? So let me help you a little bit. Here's something to help you along that thought. Could we do best score with and without an employee, but only in his or her sub-hierarchy, sub-tree? So once I figure this out, I never have to take all those possibilities in order to do the rest of the computation. So that's where it helps. The reason things got bad with that first bullet was because all these possibilities, you had to match it against all those other possibilities. You don't really need that. In the end, all you care about is, if I have a subtree here, let's say this is some subtree that's part of some larger tree, all I care about is what is the best score that I can get with or without the leader of this subgroup. That's all I care about. Can I do this? And if so, how is it going to help me?
To compute that subtree, what do you still need to do that 2 to the n, so taking or not taking?
Within the subtree, but subtrees can be small. How many subtrees do you have? So, all right, so that's actually a good question. So we have to somehow make this work out, right? Think about this subtree computation. Okay, I am going to, for every node, I am going to keep track of 2 answers. This is the score, best score for the entire subtree, but with this node. This is the same score, but without the node. And I'm going to do this at every node. Now my question is, how are all these values connected? Because if you know how they're connected, then we can write a recurrence relation. Now, is it easy down at the leaves of the tree? It is, right? So it's also easy when you get to the next level, and it gets progressively harder. But I don't care how big this tree is. If I have these values, can you figure this out?
Yeah.
Tell me how.
It's the summation of those values, or the value of that one.
Summation of what values? You haven't been, that's not clear enough.
The ones in the bottom.
So again, let me tell you, H is for with, T is for without. Now what do I mean? That's the best score you can get, but if you take this guy, whoever this person is. And this is the best score you can get, but if you don't take this guy.
So in the leaves,
Yeah. Forget the leaves. Now my question is, how do I get to that parent?
that H would be the value, T would be 0. At that.
H is with, T
Yeah.
is without. Yeah.
So if it's only a leaf, then that would be 0.
It's not a leaf. This is a subtree. I keep telling you.
Okay, so
I've done this computation for this entire hierarchy. Okay? So that's Jane, that's Josh, whatever, Jim, Jake. Josh has an entire subtree under him. And I've figured it out. I know what happens, what's the best score I can get with Josh and without Josh. Same thing with all the other guys. Right?
Okay. You, for that top node right there,
Yeah.
you know whether you should take it if h of p is greater than hc1 plus hc2 plus hc3, correct?
Okay.
So that's when you know whether you should take this for this subtree.
All right. Okay. Is that all the considerations? Remember, I'm telling you. So you need to think about this in a systematic manner. I can figure this out for every leaf. We just agreed on this, right?
Yeah.
Leaves are easy. So now I'm trying to go bottom up in this hierarchy. Somewhere at some stage in the computation, I've figured out H and T values for all these children. Now help me figure that out for the parent.
Only one.
You're understanding this now? Yeah. That's the systematic way of going with this computation, right?
Okay, I think.
Yeah.
The take the h of p
Yeah?
for this parent is going to be equal to tc1 plus tc2 plus tc3.
Fabulous. Yeah, that's correct. So H of V, So yeah, these are the two definitions. So H is with and T is without, and you just told me that to compute the H for the parent, I take all the T values because I cannot take them.
Yeah.
Right, good, perfect. Now what about the T?
The other.
Are you sure?
Oh God, okay, give me a second. T is without.
Yeah, T is without.
If it's without, it would be worthwhile taking all its children, because you could.
Correct. So what's the answer?
So would it not just be HC1, HC2, HC3?
It's like the reverse, the T is the H's added and the H's are the T's added.
Wait,
Uh,
wait, don't tell us yet, don't tell us yet. I
Yeah, it's
think
just a small
something
small
is
fix.
missing.
Yeah.
Small fix.
If you always take it, then it'll become like the other problem. Remember what I said, you take Jane, so you don't take any of this. Then you take all the guys below it, and that's all you'll get if you just do T equals H plus H plus H.
Maybe it could be the math.
Uh-huh. Why? Does that make, are you sure?
I'm gonna die on that. I'm gonna die on that. Yes. 90%.
Why?
Convince
Why
him.
choose a match
Convince him, yeah.
And the other one is like some positive value. Why would you want to take that as well? I guess this is the point.
So go back to your example, okay? Go back to your example. Now, what did you say was the, so here, you were willing to sacrifice Josh for Jack and Janelle, right?
Right.
Which means that Josh and Juan both didn't show up. You're not inviting them for the party. You're uninviting them. Is that clear?
Wait, sorry, say that again. What names did you say?
So you decided to go with Janelle and Jack and asked Josh to take a walk.
Okay, because 7.
But Juan also is not invited because Jane is. So that means both these people are not invited. Right? This is something that's complicating things. Because now we have a boss and a supervisor and an employee both not invited. Right?
Oh, damn.
Are you
I know what you're
suffering?
saying now, but
Are you suffering?
yeah. Wait, can you go back to the subtree so I can look at it?
Yeah.
Because we need to consider without taking it, because that without for the bottom nodes, without taking it, that might be a greater value than taking it.
Yeah.
So we need to
So,
consider that.
so what is your formula for?
Oh.
So you already said what H of P is.
So it would be the max. Okay.
Yeah.
Max of HC1,
Yeah.
TC1 plus max HC2, TC2 plus max.
Very good.
HC3, TC3.
Which is exactly what he said. So.
All right, but now I understand it. Sorry.
You couldn't explain it to me. Yeah,
So-
he understood.
So in the end,
Did you understand?
in the end, everyone kind of has to convince themselves, right? So this was the easy case. If P is going to be taken, if it is with P, then all the subordinates are out. So you have to take the T. That's the without, right? But if you're doing T of P, then it's one of those two. We don't know which one, right? Because it's a large subtree. We have no idea how it's going to work out. So you take the larger of those two, add them all up, because in each of the subtrees, whatever choices you make doesn't affect the other. Boom, you're done. Yeah? So can you now write code for this?
Alright, wait, let's discuss this for a second.
All right, so, or do you want to do the example first? By the way, are you clear that you're going to report the H of root if you have to take the root? Otherwise, if you don't necessarily,
Or don't take
If you don't necessarily have to take the root, then what's the answer?
The maximum of taken or not taken.
Maximum of h and t of root. Yeah?
Right.
Okay. So let's take this example and figure out whom we are going to invite. How are we going to do this?
So we know we have to take Jane.
Sorry?
We know we have to take Jane.
Again, you're not using the formula. You're thinking from an answer point of view. That's not what I want. We just figured out an approach.
Yeah.
So let's talk about the approach. What is our approach?
We start computing from the bottom.
From the bottom, yes.
Yeah,
So
the
now,
median.
that's right. So h of this is going to be 5. Width is 5. This is 11 and this is 4. What is t of this guy?
They're all 0. Yeah.
0, right? So h is 5, t is 0, h is 11, t is 0. So I can write this, right?
Yeah.
Now let me see if I can scribble on my screen. I am never good at this. Oh, I might as well do it on the board, right? Okay, so I've got 5, 11, and 4. So this is going to be 5 and 0, 11 and 0, 4 and 0. So the first number is h, the second number is t. Okay, so 5 and 11 have a parent called 6. Tell me the h and t values for this.
6, 4, 5 plus 11.
So it's either going to be 6 or 5 plus 11, right? And what about this guy? 9 or 4. And then we have 2 and 10. So this is going to be 10 and 0. This is going to be 2 and 0. Are you with me so far? And now we need so it's either going to be right? So you can take the larger of all of these, 16 plus 10 plus 2, right?
Yeah.
And that's going to be the without score,
But the width for
right? So the slash is going to be the without score is 26, 28. What is it with?
7 plus 16, no?
7 plus this plus this plus this, so that's 23.
Yeah.
Cool?
Yeah.
Okay. Then let's go up the tree here. What's that going to be?
5 plus 4.
So either 5 plus 4, that's a 9, or a 9. Right? And then I have Jane to deal with. Her score is a lousy 2. So either I take 2 and take 28 and 9, right? That would be 30, 39, or 28 plus 9. So that's 37. Okay, so actually inviting Jane worked out okay. She got a better score. So if you're forced to invite Jane, that's going to be your best answer. If you are not forced to invite Jane, you will still have that as the best answer. Now, can you write code for this? Quickly.
Oh, wait, wow. That's another constraint.
It turns out it's something like a 5 or 10 line recursive code, kind of. All right, I am kind of way past time. I have to go. So let's try and wrap this up. I'm sure you can do this because here you're going bottom up, right? So in a tree, what kind of traversal is that if you're doing bottom up? Is it pre-order, in order, or post-order? post order. Why is that? Because you're doing the children first before you do the parent. So it's post order. So you write post order traversal and then fill in put in the recurrences. That's really what you have to do. Okay. So here is my pseudocode. I'm going to write a procedure that returns two values, the h value and the t value. The parameter that it takes is v. If v is a leaf, it has no children, then you're going to return its score or 0, right? Otherwise, for every child of v, I have to do some work. What do I have to do? I have to call recursively this function. So I'm going to recursively call it, and it'll return me some values, right? And I'm going to do this one child at a time. So it turns out I can just do this and accumulate my values. So the h of the parent is you're going to add to it the t of the child. And the t of v is going to be equal to what?
Maximum of.
Right. So again, there is a plus equal to because you're doing this one child at a time. Right? Return. So even if you were to write this in whatever Java or Python, it still can't be more than 10 lines of code. Cool?
I like this one a little bit more.
Yeah. Yeah.
What was the name of the problem?
Company party.
Company party.
Yeah, it's here.
Region. Okay.
Yeah. All right, let's stop here, guys. We've had too much fun. Yeah.